You know what's really great to do right after you did a bunch of chain rule problems? A bunch more chain rule problems. So like I just made the other video for, I don't know what it was, 7 through 39 odds or something. So like the last thing I want to do right now is more chain rule problems. But that's what they're paying me for, to do chain rule problems for you guys. So let's see. I think this one might need a debatable whether this needs a rewrite. And I'm never going to stop you from trying to be a hero and cut out too many steps. I will caution you against it when I think it is a good idea to caution you against it. This one I think probably needed the rewrite. So I got a product rule here going on. So let's see, the derivative of the first times the second plus the first times the derivative of the second. And the derivative of the second, that's going to have a double layer chain rule. So that's 3 tangent x to the 1/2 squared, that's the derivative of something cubed, times the derivative of what's inside. Derivative tangent of whatever is secant squared whatever. And the derivative of x to the 1/2 inside that is 1/2 x to the negative 1/2. And that just barely fit on the screen. Okay, it was meant to be. Number 30. Geez, who makes this stuff up? Now, if you're looking at this, at these trig functions, thinking, oh, sine over secant, maybe that could simplify. It can't, because it's the sine of x on the top and the secant of 3x plus 1 on the bottom. So those, nothing you can do there. Just take a deep breath, dive in. So let's see, low d high minus high d low. And the d low is going to have a chain rule. It's only going to pop out of 3, but it does have that chain rule in effect. So derivative of secant of whatever is secant of that whatever tangent whatever times the derivative of what's inside. If you're looking here and saying, wait, there's two different what's insides here. No, there aren't. It's the what's inside of this. This is the thing that you're taking the derivative of. You're not taking the derivative of the thing like that you're writing down while you're doing the derivative. This is not the thing you're taking the derivative of. It's the one step before this. So that's all there. How about the sine of tangent of 3x? They didn't put that tangent of 3x. That's not in parentheses, but I would write that. So I'm just going to do a little rewrite for you here. So we can just see the two layers so we know what to expect here. Alright, so the derivative sine of whatever is the cosine of whatever. And the derivative of what's inside there, well, the derivative tangent whatever is secant squared whatever. And the derivative of what's inside that is 3. You know what the derivative of 3x is? It really is just 3. So we're done. And we also rewrote it, so we knew what to expect there. It'd be funny to like do a some kind of satire, I guess it would be, of a modern day update of the whole Trojan horse thing. But instead of a Trojan horse, it was like a giant Matryoshka doll with Vladimir Putin hiding inside it. I think that'd be funny. Maybe just a cartoon. Maybe like the full-blown thing. It's not really that much there. I think that this, maybe, I'm looking at that thinking because it's the same thing inside, is it worth trying to mess with that? And I'm quickly deciding that no, it's not. Not going to do it. All right, so let's see. If that could be simplified into something much simpler, then I don't know why I wrote that one out, because I didn't really do anything to that. Oh well. So quotient rule. I've got now low d high. Derivative of 1 is 0, and then the derivative of cosecant of whatever is minus cosecant whatever, cotangent whatever, times the derivative of what's inside that, which is 2x. Okay, so let's, especially, like, the more complicated the rule is with quotient rule, I just got to check in here, make sure I understand where I'm at. That was low d high. That's where I'm at in the quotient rule. Minus, I have a similar looking thing to that here when I do my high d low. So the derivative of minus cotangent squared is cosecant squared of x squared times the derivative of what's inside that. Over low. All right, so I don't know. It wasn't that hard. It's just messy. All right. Looks like we got like quotient rule and what did I say? Quotient rule. Jeez. Looks like we got product rule. That's the other thing. That's what it's called. When you have a product, you use the product rule. And I always think it's a good idea to do the rewrite on those. Okay, so product rule, and then within that I'm going to have some chain rule going on. So dy dx is equal to the derivative of the first, 5 times x squared plus x to the fourth times 2x plus 1. You getting pretty good at this chain rule thing? Times the second. So that's my derivative of the first times the second plus the first times the derivative of the second. So again, the real rookie move here is to do the 8 times whatever to the 7th, but to make this a cosine on the inside also. But you have to, it is a separate step. You do not mess with the inside on that first move. 38. I'm feeling this one. I'm going without the rewrite. Okay, so the derivative of whatever to the 17th is 17 times 1 plus x squared over 1 minus x squared to the 16 times the derivative of what's inside, which is a quotient rule. So that is low d high minus high d low all over low. All right. There's something that's going to probably, let's see, minus 2x cubed plus 2x cubed. Those would cancel. You can simplify some there if you want. Number 40. Ooh, many layers, many layers. Let's see, this needs a rewrite. All right, this is, I think, 4 levels of Matryoshka here. 1, 2, 3. Oh, maybe just 3? Why did that seem like more? Well, let's see. Let's see how this plays out. Maybe just 3. But I guess 3 is more. That's the most we've seen, isn't it? Okay, so I guess I'm sort of counting the first thing as a layer, right? Because there's always like the doll itself. Like you don't know if there's going to be more layers inside. So there's the original doll, and you open it up, and if there's nothing inside, then there wasn't any chain rule. So there's that one. So I guess there are 4. So like that's like the first thing here. So that's like your derivative, and then this one I think we're expecting 3 more, right? Oh, time's up. So derivative of something to the 12th is 12 times that thing to the 11th times the derivative of what's inside. So the derivative of what's inside that 1 is gone. And then the derivative of something to the 3rd is 3 times that something squared, and then the derivative of what's inside that, I guess I can close that. Derivative of what's inside that, derivative of sine of whatever is cosine of whatever, and then the derivative of what's inside that is 5x to the 4th. So there's my outermost layer, and then 1, 2, 3 more to go with my 3 layers. All right. Oops, can you see that 5x to the 4th there? There's the whole thing. 42. Here, a question, sometimes an answer. Oh my goodness. Oh, you know what? This is one of those CAS problems. I should have told you X-nay on the 42. There you go. Maybe that if you know the Hitchhiker's Guide to the Galaxy, the answer to the question of ultimate question of everything and whatever. Maybe the question was what is the number of the problem in section 3.6 that I don't have to do? Maybe that was the question. So look at us, just got a little closer to the finish line. Hey, tangent lines, got to know how to do this. So let's see. I'm going to make an equation for a tangent line to that at x equals pi. To write the equation for a tangent line, I need a point and I need slope. So my point, first of all, is going to be pi, comma, what do I get when I plug pi into this? Cosine of 3 pi is -1, right? And times pi, so that's negative pi, I believe. And the slope is for my derivative. So the product rule, derivative of the first is 1 times the second plus the first times the derivative of the second. Derivative of cosine whatever is negative sine of whatever times the derivative of what's inside that. Right? Think I'm good? So dy dx at x equals 1. That's a notation that we're going to see sometimes in the book. Make this big. That's just a big straight line. Dy dx at x equals 1 is cosine of 3 pi. We just did that, right? That's -1 plus pi times, but let's just see. I have a feeling this is going to all go away because isn't the sine of any multiple of pi is 0. So this whole thing is going to get wiped out. So my slope is just -1. So in point slope form, I have y minus y equals slope times x minus x. There's the equation for my tangent line. If you are not on board the point slope train, You need to, next time we pull into a station, this is the 3-6 station, you should hop on board. It's the way to do it. Number 46, another tangent. Oh no. Oh, you knew it. You knew it, and you didn't even tell me. I can't believe you did that to me. Well, there's a little bit of extra practice for you. You saw that the whole time. You were like yelling at the screen, weren't you? All right, so I guess I'll actually do number 44 now, which is, that was mean. I thought we were friends. All right, at x equals, I see how it's going to be. So let's see, plug the -3 in here. -3 to the third power is -27. That's a sine of -26, whatever the heck that is. And, you know, sine's an odd function, so I think in the book they decided to flex their trig knowledge here. If you have an odd function, the sine of -26 is the same as negative sine of positive 26. That's because it's an odd function. It's because the sine function looks like this. It is symmetric with respect to the origin, which means if you flipped it like 180 degrees around the origin, you'd get the same thing. And one of the properties, one of the things that implies, is that if you have the sine of some negative thing, that's the same as going to the positive side and going the other direction, up, down. So in other words, if you plug some number in and you get some y value, well, if you plugged in the opposite of it, you would get the opposite of it, right? So that's a thing. So I think in the book they might have done that. Just telling you that, so if you looked in the back and you were confused about it. All right, what's the derivative of this? dy dx is equal to derivative of sine whatever is cosine of whatever times the derivative of what's inside. All right, so when I plug -3 into this, I get the dy dx at x equals -3 is cosine of -26 times 27. Okay, and likewise here, the cosine of -26 is the same as the cosine of positive 26, because cosine is an even function, and that's a property of even functions. So I don't really care, like if this was a quiz question or whatever, you wouldn't have to do that, but I just want you to understand that that can be done. All right, so here's my point, except I think they're going to use this version of it. So this is my y minus y equals the slope times x minus x. All right, 46. I'm going to try real hard to do the right problem here, because I know you guys aren't going to tell me. I'm on my own. X minus x to the -1 cubed at x equals 2. All right, so let's see. My point is x. Oops. I know what the x value is. It's 2. 2, comma, what do I get when I plug 2 in here? Let's see. I get 2 minus a half, which is 3 halves. And then if I raise that to the third power, that's 27 eighths. I think I'm good there. That's 2 minus a half, that's 3 halves, cubed. 3 cubed is 27, 2 cubed is 8. All right, so that's my point. Dy dx is equal to the derivative of something cubed is 3 times that thing squared times the derivative of what's inside. Okay, so what do I get when I plug 2 in to that? Well, I know that this expression is 3 halves, right? So 3 times 3 halves squared is 27 fourths, I believe, plus, times 1 plus 1/4 x to the negative 2. That'd be 1/4, so it's 5 fourths. And ain't no canceling that can happen there. So 5 times 20 is 135. All right, and I mean, you're like, oh, math. But now if you're doing point-slope form, you're done. You just have to write it. Y minus 27/8 is equal to 135/16 times x minus 2. Right. Great. We're going to come back to this one and just show you something with the calculator. Not that you're allowed to use your calculator, but just to kind of check our answer there. Give you a good visual. Oh, come on. Who's making up these problems? Cotangent? I hate cotangent. I'm just kidding. I don't really have any strong feelings about the trig functions. Okay, can we evaluate this without a calculator? Well, let's see. Cotangent is tangent upside down. What's the tangent of pi over 4? That's just 1. So the cotangent would be that flipped upside down, which is still just 1, to the 4th power, still just 1, times 3, still not 1. No, not 1, 3. So my point is pi over 4 comma 3. The derivative of this, so as I can find the slope, is 12, that to the 3rd, times the derivative of what's inside, is that. Okay, now I gotta plug pi over 4 into this. So pi over 4, that's just 1 still. So that's 12 times 1 cubed, which is 1 times, let's see, the cosecant of pi over 4. That's upside down of sine, right? So the sine function at pi over 4 is the square root of 2 over 2. So if you flip that over, that's 2 over the square root of 2. But of course, 2 divided by the square root of 2 is just the square root of 2, right? Because, I mean, 2 is... okay, so I got the square root of 2, but then I'm squaring that. So that's 2. And then I'm putting a negative sign in front of it. So, all right, this is at x equals pi over 4. So I'm pretty confident that I didn't mess that up. And now I can write the equation for the tangent line. And I'm going to put a box around that one, just randomly, which I didn't do with any of the other problems. And let's see, the last one, I wonder if I can, instead of starting a new sheet of paper. Was I supposed to go to 50? I was, okay. So let's see if we can do this last one in this space here. I think I'm going to write it so as to avoid the quotient rule, I'm going to write it like that. So at x equals 0, when I plug 0 in here, I'm going to get 0 at 0 times 1. And then when I take the derivative, I'm going to use the product rule. The derivative of the first is 1 times the second plus the first times the derivative of the second. Derivative of something to the negative 1/2 is negative 1/2 times the something to the negative 3/2 times the derivative of what's inside. All right, so notice that when I plug in 0, this whole thing gets knocked out, right? So as messy as that is, just because of that first x, this gets knocked out again here. But this does not. This dy dx at x equals 0 is 1. Right? So it looks like I got the line y equals x. Right? Goes through the origin, slope of 1. Seen that line before. All right, so you can cut this off now if you want. I just want to show you something with a calculator that's kind of cool. A way of checking your answers. So look at 46. We got this crazy equation for this line. Not that crazy. I mean, it's got fractions in it. Whatever. So let's clear this junk out. So I'm going to go ahead and put this function in here. X minus x to the negative 1 cubed. And I'm also going to put in the tangent line. I'm going to have to, of course, this is y equals, so I'm just going to have to add that over there. No biggie. By 16 times x minus 2 plus 27/8. Right? And then before I hit graph, you could do that now, but before I do that, I really want to have a window where this point right here is like right in the middle of the window. So let's see. If my x-coordinate is 2, then 0 to 6, that's fine. If I really want it to be right in the middle, you go 0 to 4. And then if I double this, just like I doubled this to get my max, if I went from 0 to double that, doubling this would be 27 over 4. And 27 over 4, well, 28 over 4 is 7. So how about that? How about I go up to 7? Something like that. That should do. And then I'm going to graph. And let me, before I do that, I think I put this in simultaneous mode, which means it's going to graph the curve and the line at the same time. So if all goes well, then right at this point, which should be right in the middle of my screen, I should have my tangent line coming through and just being beautifully tangent to the curve, whatever that looks like. So here we go. Hope I didn't mess it up. Cool. So there it is. The point of tangency is right there, right smack in the middle. You can see the line and the curve. So that looks great. And if you had done that in the standard window, I think it probably would look pretty okay too. Oh, not nearly as good, because this is a vertical asymptote. Oh, that's garbage. Ours was way better. All right, that's it.